Hi there, I'm Rasmus Båth, and thanks for tuning into my presentation, 3 strategies to tackle big data in R and Python. Now, I don't know if you remember big data. It used to be kind of the buzzword a couple of years ago. It used to refer to this huge amount of data that these then cool companies like Facebook and Google and Twitter were amassing and kind of all the promise that this data brought. Now, I don't think big data is a buzzword anymore, and I have the data to back that up. So if we look at Google search trend, for example, we can see that big data kind of peaked somewhere around, 2017 or something. And if we look at Stack Overflow trends, like what tags people use when they ask questions on Stack Overflow, we can also see that questions tagged with big data also peaked somewhere around 2016, 2017. So looking at this, it seems like the big data era is over, but I don't think that's the case. If we instead look at a questions tag with some big data tools, some tools you need to use when you have big data problems, then the picture is different. So here, for example, we have the trend for PySpark. Spark is a tool you use to handle big data, and you can just see that it goes up. The same thing is we see if we look at some of the big data warehouses. So questions tagged with BigQuery or questions tagged with Snowflake, those are also trending upwards. So even if big data might be over as a buzzword, I still think that big data as a problem that data practitioners out there need to solve, that's still around. Now, in this presentation, we will look at 3 strategies to tackle big data. Strategy number 1, use a local database, say DuckDB. Strategy number 2, use a computational engine, say Spark. And strategy number 3, use a data warehouse, say Snowflake. Now you might wonder, why would you need any strategies at all to tackle big data? And I can show you that with another graph. So here's another graph. On the x-axis we have year, and on the y-axis we have what? Well, on the y-axis we have how annoying big data is the first time you encounter it, and as you can see, it's equally annoying independent of the year. So why is it annoying? Well, if you have big data, suddenly you can't use your normal toolbox anymore. Data is big. It's too big to use R and the tidyverse or Python and pandas. So all the tools that you learn are not useful anymore. What should you do, And then if you want to use something else, it's not always clear what to use. There are like a plethora of different tools, and whichever you're going to go for, it's likely going to be slow and or expensive. So that's why you need strategies to handle big data. Now, like if you Google big data, you're going to end up looking at pictures like this. It looks like big data is this blue ball of promise, and it looks like the Matrix. Or if you use one of these AI tools that generate images for you, you get the same. It's this basic big data is basically like you're stepping into the Matrix. However, I don't think that's how big data feels at all if you're a data scientist or data analyst. Big data feels more like this, I think. Like it's just super annoying. It's slow. It makes you want to bite your laptop. I don't know. Like this is how big data feels. And that's why you want strategies to handle big data. Now, we haven't really talked about what big data is. Like, is this big data? Yeah, maybe it was, at least. Like if you had data in the 80s that was so large that you needed 2 floppy disks to hold it, then you had a big data problem, because your computer back then probably only had 1 single disk drive, but you have two floppy disks, you didn't have a hard drive, then you had a problem. The data was so big that it was hard to compute on it. And I think that's the general good definition of what big data is. It's data that's so large that it's hard to compute on. And if you're doing analysis on a laptop today, data that's hard to compute on is data that don't fit in your working memory. So if the data is larger than your RAM, your working memory, then I think it's big data. Now, that's of course a moving target. If we look at this graph, we see that the average amount of RAM in a laptop has, it steadily is going upwards. And if we look at this, I would say if your data set is more than 8 gigabytes, then it's pretty big. I would call that big data. And by the way, here is another picture of how big data looks. This is how it looks when you try to load in big data. your memory pressure just goes up into red, and then everything grinds to a halt and nothing works anymore. Yeah, this is another view of how big data it could look. Now, fitting the data in memory is just one of the problems with big data. There are a couple of other ones. Like, another problem is that you ideally want to process your data using some kind of multi-core approach. Like, if the data is big, but you're only processing it using one single core, then it's likely going to be pretty slow. A third problem is that there's probably a reason why the data is big to begin with. Like, data just doesn't go big by itself. Normally it gets big because it's the result of some kind of process that's continuous and ongoing. For example, it might be logs from a website or something that produces a lot of data over time. And that means not only do you want to process all this big data, but you also want to process the latest big data. So ideally, you need some kind of process to keep this data fresh and up to date. I think it's rare to have big data that you can put on a hard drive and then that's it. Usually you want the latest big data, and the latest big data is the data from today. And the problem is that Python and R, they don't really help you with any of these problems out of the box. All right, so now we're almost at the point where we can talk about these three strategies for how to tackle big data. The only thing we need first is some big data to tackle. So here I pulled down the Spotify charts dataset. It's a pretty cool dataset with all top 200 and viral 50 Spotify top lists, not daily, but almost daily from different regions around the world. It's 25 million rows, 3 gigabyte CSV file. So it's not really big data. Maybe it was like big data around 2010, but I think it's big enough for now. So here is a snapshot of how the data looks. So each row is a song, the rank it had, a certain date, in a certain region, and what the name of the artist was, and so on. 25 million rows. And the question we are going to ask of this data set is, which artists have spent the most time on the Swedish top 200 chart? And before we go into the big data approaches to this, let's just answer this question using normal R tidyverse and Python pandas code. This won't really run on the whole data set, but here is at least how we would answer this question using tidyverse and pandas. So if you like R, look to the left. If you like pandas, look to the right. All right. So first we load in the packages we want. Then we read in the data set. But now since the data is large, let's just take the first 100,000 rows. And then it's always good to take a look at how this data set looks. But now with the charts data set, we first gonna look only at the top 200 top list and only in Sweden. And then for each artist, we're gonna figure out how many distinct dates this artist has spent on the Swedish top list. That will be how popular this artist is. And then just for fun, let's also figure out how many distinct songs this artist has. And then we want the artist that's been the most on the Swedish top list to be at the top. And then we want the top 10 artists. And if we run this in R, here's a snapshot, or here's the data set, how the first couple of lines looks. I recognize some artists at least, Shakira there, for example. And then if we run this only with 100,000 rows, we get these top 10 artists, where I don't know if I recognize some of them, but they're not the top 10 artists that I would expect, because we only used a fraction of the data set. Right, now we're ready to look at the first strategy, use a local database. So, use a local database. This strategy means that you fire up a local database engine that can compute on the data on disk, not only in memory, and then you interact with this database from R and from Python. Here there are many different databases you could choose from. You could go with something like PostgreSQL, old and stable database, or SQLite, a lightweight database that runs in process. But here we're actually going to go with DuckDB, which is a database that's especially made for this purpose, to analyze data. So what is DuckDB? It's a newish open source project created around 2018 They describe themselves as an embeddable in-process column-oriented SQL OLAP RDBMS. That was a lot of jargon there, but if we break it down, we can see that it uses SQL, the structured query language, to instruct this database what queries that you want to run. It's an OLAP database. It's a database for online analytical processing. That is for data analysis, so that's exactly what we want. It's a relational database management system. That basically means it works on tables, which is basically a data frame, so that's what we want. And it's really easy to install and runs just inside R and Python. It's basically just a package install, and then you have all the power of DuckDB at your fingertips. Now, there's one thing here, and that's you don't program DuckDB using R or Python. You program it or instruct it using SQL. So that means we have to take our query here and we have to translate it to SQL, which actually looks fairly similar to the tidyverse and the pandas queries that we have. So from the charts data set, we only want Sweden and the top 200 top list. We want to group by artist as before. And then we want to select the number of distinct dates this artist has been on the top list, then the most popular artists on top, and then only the top 10 most popular artists. So as you can see, this SQL code, fairly similar to the R code and Python code, except that at some point in the 70s when SQL was created, they decided that the from statement cannot go on top. The select statement has to go on top. So actually, this is how it looks. Except that I have to tell you that DuckDB is a pretty awesome database, and they just released a new version where you actually can do it like this, have the from statement on top. But normal SQL has to be written like this, with the select statement on top. All right, now we have our query. We have translated it to SQL, and now we can actually fire up DuckDB in R and take it for a spin. So first, let's load in the packages we're going to need. We're going to need the DuckDB package, obviously, but we're also going to need the DBI package. So the DBI package is an interface, a database interface package that implements a bunch of functions that are useful when interacting with different databases. So the cool thing here is if you learn the DBI package once, you can use the same set of functions when interacting with many different databases, including DuckDB. So for example, DB Connect, that's part of the DBI package. So here we're connecting to DuckDB, which is going to create a DuckDB data file on disk where all the data we put into DuckDB will be stored. And now we can execute queries on top of DuckDB. So for example, here we execute a query that takes the data in the charts CSV dataset and reads it into the charts table in DuckDB. And now we can, for example, take a sample of 10 rows and show that. So this is roughly the same as running head in R. And now we're set up. We have all the 25 million rows loaded into DuckDB, and we can run the query that we compiled before. And on my laptop, this takes maybe a second to go through 3 gigabyte CSV file, which I think is fairly amazing. And the result is this. So here we have the 10 most popular Swedish artists: Hovet, Avicii, Ed Sheeran, Lale, etc. Some of these are international, but some of these I think are pretty local to Sweden. Now, I said that you have to use SQL to interact with DuckDB, but that was actually not really true, thanks to a really cool package called the dbplyr package. So thanks to that package, you can convert the charts table in DuckDB like this, and then you can actually run dbplyr or dplyr commands on top of it as if it was a data frame. So here DuckDB is not the data frame. It's actually still a table in DuckDB, but thanks to the awesomeness of the dbplyr package, you don't even notice that. I think this dbplyr is an amazing package. All right, that was the first strategy, and there are some pros and cons with using something like DuckDB. So pros: super easy to install. It's basically just a package, runs locally, uses your CPU and your disk to max. It performs amazingly well, and it's actively developed. Some cons, like you're stuck with SQL or dbplyr. If you have some custom R functions that you want to run on top of big data, DuckDB is not going to be that helpful. Like it runs locally only, and there's no easy hosted option. Like if you have a tiny little laptop, it's not super easy to run DuckDB in the cloud on large data. And it's a fairly new project, so while it's actively developed, that also means things can change. So if we score it on how well it solves these three problems, I will say it solves the memory and parallelism problem, half of that at least, because it's kind of still limited to the computer you're running it on, and it's not super easy to run it in the cloud. But otherwise, pretty amazing project, DuckDB. All right, strategy number 2, use a computational engine. So this strategy is that you fire up a local computational engine, whatever that is, that can compute on the data on disk and not only in memory. Or you fire up a remote computational engine on a really beefy machine, like on Amazon. You can get the 384 gigabyte 96 CPU instance. That's a pretty beefy machine. And then you control the engine from R and Python. So here it's not a database anymore, it's a computational engine, so it's something that's more flexible. And here there are also a couple of different options you can go for. You can go for something like Dask in Python, or Flink and Apache Spark that works both for Python and for R. And here we're going to go with Spark because I think it's the most established one. So what is Spark? It's a large, stable, open source project launched in 2012. They describe themselves as a unified analytics engine for large-scale data processing, and it does a lot. Spark does a lot. It's not only, you can not only use it as an SQL database or a processor. It does machine learning, streaming, can do graph computation, and you can use it also to run custom Python and R functions on large data. It's possible to run locally, but it's kind of common to pay a cloud service to run it for you because it's a little bit of a headache to set up Spark. Something like Amazon EMR or maybe Databricks. So let's do the same thing we did in DuckDB, but now using Spark. And there are two ways you can connect to Spark. It's the official Spark package, but then there's also the very awesome Sparkler package from RStudio/Posit. And I really recommend that way of interacting with Spark, and that's what we're going to use here. So we have installed Spark before running this, and we now connect to a local instance of Spark using the Spark Connect function. We read in the CSV file, and now we can mostly use dplyr functions to interact with this data set as if it was a data frame. So here we take a look at the first 10 rows, for example, and then we can just run dplyr code on this as we did before. So to be honest, this is going to be a fairly boring demo because it's going to look extremely similar to the DuckDB demo. And here again are the top 10 artists in Sweden. I can tell you that on my laptop, this is actually a fair bit slower than DuckDB. And that's generally my impression. Spark is fairly slow on mid-sized and small data, but where it really shines is that if you have huge amount of data, Spark can often handle that still. So it scales very well. But as before, I mean, you can use dplyr to interact with Spark, but it's also an SQL engine. So if you only have, or if you like SQL and you are setting a lot of existing SQL statements that you want to run on big data, Spark can handle SQL as well. So there are some pros and cons with using something like Spark. Like, as opposed to DuckDB, with Spark, like, you get it all. It's SQL processing, machine learning, streaming, etc. It's possible to run it both locally, and there are many good hosted options. It connects to many different data sources. There's a large community. Spark is battle tested. It's used by a lot of large companies. So, but even if it's possible to run it locally. It's not necessarily easy to run it locally. It requires the correct version of Java. It's kind of fiddly. There's a lot of options, and they are not usually set to good defaults out of the box. And if you go for hosted, it's usually kind of expensive or a little bit fiddly. And yeah, there are a lot of options, and it's fairly small it's fairly slow on small data. That's some pros and cons with using Spark. So since there are hosted options where you can get these huge machines with 96 gigabytes of RAM, I would say it gets a full check mark on memory and full check mark on parallelism. When it comes to helping you out with keeping your data fresh, it gets half a check mark because it doesn't solve that out of the box, but at least it connects to many, many different data sources, so it kind of helps with this a bit. All right, last strategy, which is use a data warehouse. So this strategy is that you use a cloud database engine that's purpose-built to handle big data workloads. And then you interact with this data warehouse from R or Python. And here I think there are actually only two contenders that matters currently. Maybe things will be different in a couple of years, but right now I think the two big contenders in this space is Google BigQuery and Snowflake. In my opinion, both pretty good products. Here we're randomly gonna go with Snowflake because I have some experience using Snowflake. So what is Snowflake? It's a commercial service launched in 2014. They describe themselves as a cloud-based data storage and analytics service. So it's a database, so you have to interact with it using SQL, but Snowflake does have a pretty advanced SQL dialect that allows you to do a lot of different things. They became kind of famous because they separate storage and computing. So you pay separately for the data that you store and the compute that you do on this data. It's not baked into one single thing. They describe themselves as petabyte scale, and that's really my impression. Using Snowflake, you can really compute on huge amounts of data, and Snowflake will handle that. So let's do a Snowflake demo. Unfortunately, this is not going to be so easy. You can't just start up Snowflake. First, of course, you need to get a trial because this is a commercial service. So you need to actually get an account. And if you look at this, you get a bit suspicious because you think it's going to be pretty expensive if you if you get $400 worth for free. Then it sounds like it's going to be an expensive service, and that's likely how it's going to be. Right, let's get started. No, actually, we also need probably to have a cloud account somewhere on maybe AWS or Google Cloud in order to get some data into Snowflake to begin with. So we will get that account as well. All right, and then we upload these charts data sets to say S3 data storage on AWS. And then we load that data into Snowflake, and now we're ready to do a Snowflake demo. So a little bit more work to set this up than working with DuckDB or even something like Spark. And now, first, we need to do some more work because now we're not doing computation on our own laptop anymore. We're doing computation on a server somewhere in the US probably. So we have to use a special database driver. We have to give Snowflake our credentials so we finally can connect. But after this, everything looks basically the same as for DuckDB. We can run queries using the DBI interface, and these queries look the same and are blazingly fast, even though the server is probably somewhere in the US. So this takes 1 second to run and get the result to my computer. Now, the only difference here is that I haven't really gotten dbplyr to work well with Snowflake. I know there is some package out there that supposedly works with Snowflake, but I didn't really get that to run. So right now, I think, at least from my experiences, Snowflake is SQL only. So some pros and cons with using something like Snowflake. Like, it's a really advanced SQL engine. There's a lot of things you can do, even if you're stuck with SQL. It's fully hosted, low maintenance. It's it truly is petabyte scale. It works with many different cloud service providers, not only AWS, but with Azure and Google Cloud. It has a pretty nice web interface where you can type in queries and try them out. And it basically connects to anything and everything. Now, it's still SQL. You're kind of stuck with that. And there's no way to run this locally on your laptop. Like the vendor login is complete. It's petabyte scale, but it's kind of also corporate scales. It's a lot of corporate stuff. And sure, it works with many cloud service providers, but I guess you need a cloud service provider now. That maybe wasn't something that you planned on getting today. And it can be pretty pricey if you don't set up things correctly. So that was some pros and cons with Snowflake. Similar to Spark, I think it completely helps you with the memory and the parallelism thing, and it gets half a check mark on freshness because it connects to many different data sources. All right, so that was 3 strategies to tackle big data in R and also Python. Here I mostly showed the R code, but the Python code is very, very similar, and all of these 3 tools or services work equally well in Python. Now, you might have noticed that these 3 tools also have something in common. Did you notice what that was? Well, it's that they all use SQL as the interface language. I think it's fairly amazing that this old database query language from like the 70s is now the modern lingua franca for big data computation. All right, that was it, except for one last conundrum, and that's the question about Journey. Did you notice that? Maybe you didn't, but if you look at the top 10 most common popular artists in Sweden, you see that Journey is one of these artists, but as opposed to all the other artists, they only have one single song. Like Avicii has 52 songs, and Ed Sheeran, he's had 59 songs on the Swedish top list, but Journey just had one single song, and still they're on number 6. So let's figure out what that one song is. Let's pick all records from this database where artist is Journey, and we get that it's Don't Stop Believing. And if I didn't put this up on YouTube, I would probably play that song right now, because it's a pretty good song. At least we in Sweden seem to think so, since it's on the top list like every single time. All right, thank you so much for coming to this presentation on 3 strategies to tackle big data in R. I'm Rasmus Båth, and thank you so much for watching.